This is now 9:06. I think we are good.
Oh, 9 to 6. Sorry about that.
No problem.
No, that's okay. We have, one is cancelled, so
Oh,
we have,
absolutely.
we have enough time here. So I would like to take this opportunity to invite Gaurav Rajan on the topic. His presentation is Influence of Cryo FSP on Microstructural Evolution and Mechanical Behavior of Still Cast AA5083 Silicon Carbide Nanocomposite. Gaurav Rajan, Suhrit Mula from IIT Roorkee, and Gaurav Rajan is a PhD researcher scholar and at the Indian Institute of Technology, Roorkee, India. He has done his master's in material science and engineering, and he has been active in the severe plastic deformation, friction stir welding, stir processing, microstructural property correlations, and failure analysis and strangling mechanisms in AA5083. I welcome Gaurav Rajan to present his talk. Thank you.
Thank you.
That cannot, that come, that is not. Okay.
Thank you very much, Session Chair. My name is Gaurav Rajan and I am from IIT Roorkee, India. So today my presentation topic is influence of cryo-FSP on microstructure, evolution and mechanical behavior of steel car 5083 silicon carbide nanocomposite. So it is about me. First of all, I would like to thank the entire fraternity of MST and organizing team for giving opportunities to present my work in front of you in the Greater Columbus Convention Center. Thank you. I am doing PhD from IIT Roorkee and my background is metallurgical and materials engineering department. And I would like to also thank my co-author and my supervisor, Dr. Suhrit Mula. He is an associate professor in IIT Roorkee. And my research interest is aluminum 5083 alloy and the processing method is friction stir processing. So this is the brief outline of my presentation. Firstly, I will discuss the importance of aluminum alloys like 5083 alloy, and then scope of aluminum alloy based nanocomposite, then fabrication methods that been used for produce the aluminum nanocomposite, and then present work objectives and methods and materials, then result and discussion, and some summary, then acknowledgement. So this is the importance of, as we all know that aluminum is a very good material to use in versatile fields like aerospace industries, naval industries, transportations. So basically the benefits of aluminum alloys are the high strength to lightweight ratio, good formability, recyclability and low density properties. These are the common properties of aluminum alloys. On these properties, the aluminum alloys has been classified on different types of alloys, which is generally based on alloying element. Like if we add the copper, manganese, silicon, magnesium, zinc in the aluminum alloy matrix, then the series of the aluminum alloys has been decided. Like all the series starting from 2000 series is having the alloying element of copper. And similarly for manganese, the 3000, silicon for 4000, magnesium for 5000, and the combination of magnesium, silicon is 6000, and the zinc for 7000, and other elements like lithium we can produce like 8000 series. So basically my focus is on the 5000 series, which is having the dominating materials like magnesium. So it has the superior corrosion resistance properties. So we proceed for this material. So these are the common applications of 5003 5083 alloy, and these are basically used in naval structural parts, like basic structure of parts like hull, deck, and some stiffeners, and some ladder and keel parts. So these are the major applications of 5083 alloy. And these are the diagram, you can see the various structures. So basically my purpose to develop the aluminum alloy based nanocomposite. So firstly we have to know about what are the conventional nanocomposite and what are the problems we are facing. So these are the problems like micron size, we are using microns as reinforcement, and some poor bonding between the reinforcement and the matrix, and some ductility, less ductility and inferior mechanical properties. So that to overcome all the difficulties occurring in the conventional nanocomposites, so conventional composite. So we are going for nanocomposite. So there are some reinforcement and some matrix material. So reinforcement is based on like the shape and size of reinforcement, amount of reinforcement, and what are the condition in which we are adding into the matrix. So, and what are the benefit we are getting from the aluminum alloy based on nanocomposite? That is, the small amount of nano reinforcement are used, and some good strength, like in particle and matrix bonding is better. And strengthening, we are getting more strength in case of nanocomposite because they are decreasing like interplanar spacing between the particles, and which increase the strength, and also dispersion strengthening we are getting. So these are the common methods used for fabrication of the aluminum composites, like liquid state processing, solid state processing, and other processes. So in liquid state, the stir casting is a common process, and which is bulkily used in lots of industries, like Swiss casting and centrifugal casting are the other liquid state processing method for the fabrication of aluminum nanocomposite. And in solid state processing, we are directly using powder on the matrix, then we are using friction stir processing, then powder metallurgy, in which the powder of aluminum and reinforcement are mixed and melt, and then we produce the aluminum and composites. And other methods is a combination of these methods, like compo casting and in situ reaction. These are the other processes. But here I choose, we develop like a combination of stir casting plus FSP. So this is my work is only based on this stir casting plus followed by the FSP process. So what are the what are the benefits of this combination? So firstly, I will tell the difficulties we are facing in aluminum nanocomposite by the normal method. If you are using single method like stir casting, friction stir processing, so difficulties are we are getting non-uniform distribution of reinforcement within the matrix, and the poor wettability, and some lack of material matrix continuity, and some also cluster and voids are formed. So overall, it did not give the better mechanical properties which related to the microstructure property. So in the stir casting plus FSP method, we avoided the voids and porosity, fine decrystallized structure are obtained, and uniform redistribution of the reinforcement particle has been achieved. So obviously the improvement in mechanical properties with respect to microstructure properties. So in this method, we already perform work, and we are getting more improved strength. But there is some coarsening of grain and precipitates are occurring. So to reduce this occurring of this coarsening and grain growth, we are going for cryo-FSP to control the rate of cooling after the FSP. Like we are using here, you can see in figure, there is a backing plate of copper below the copper plate. We are flowing the liquid of ethanol plus liquid nitrogen, which is around 35 degrees centigrade. So by this method, we are real time we are controlling the cooling of heat generated during the FSP. Like you can see that the figure, the tool is rotating and the plate is mounted, and then we are proceeding to the traverse direction. Then heat is controlled, and we are getting obviously the better grain refinement properties, ultra fine recrystallized microstructure, improvement obviously in mechanical properties. Later on I will discuss my work. and the more uniform distribution of precipitates. So present work objectives are that development of silicon carbide reinforced aluminum 5083 alloy nanocomposite by using this method, stress casting followed by cryo-FSP. And then after producing the nanocomposite, we are going for characterization like microstructure properties and mechanical properties. Microstructure properties like through OM, SEM, EBSD and TEM analysis. Investigation of mechanical properties like tensile and hardness properties of silicon carbide reinforced nanocomposite. And obviously, after doing this tensile test, we are going for fractography study and strengthening mechanism we have been studying. So here we can see that two diagrams. In left diagram, firstly, I made the nano reinforcement. We purchased the micron size reinforcement, which is silicon carbide. I analyzed the size of powder, that is 40 micron around, and then we did 50-hour ball milling. After 50-hour ball milling, we got the nano reinforced particle of silicon carbide. That is around the 80 nanometer on average. Then we have characterized TEM analysis and the XRD analysis of the nano reinforced silicon carbide powder, and we confirmed that from the interplanar spacing the silicon carbide particles. And there after we did FSP process. So this silicon carbide powders has been added through the stress casting process in the aluminum matrix, then go for the FSP method. Though in previous slide I show the diagram here, so we arranged the setup, we made the setup like this. Below the copper plate, the flow of liquid nitrogen plus methanol has been flowing, and some temperature measurement like a data logger has been used to check what the changes occurs in the temperature. So all the setup is made in our lab, and these are the process sample. I am showing in this right side, you can see. So after getting the data of temperature, we observed that in the room temperature we are getting the peak temperature of 440 degrees centigrade, and after using the cryo-FSP method, we got the drop of around 50 to 60 degrees centigrade. And in the peak temperature through the nugget zone, and nugget zone I inserted the thermocouple through the nugget and transition. So these are the same position, and the drop is around 50 to 60 degrees centigrade. Then after we gone for microstructure evaluation, firstly we did optical micrography as cast material without reinforcement, A figure, and in B figure you can see the composite material but without FSP. Then in third, room temperature FSP after stress casting, and D figure is shown microstructure of cryo-FSP after stress casting. So we overall got the fine structure, microstructure, but we are not getting clear data of what are the grain size, what are the orientation, what are the morphology of the precipitate and the added nano reinforcement. So we go for EBSD analysis for better understanding of the grain size and other misorientation. So we did EBSD of the longitudinal direction and normal direction. So they are the four dominating zone. We got like nugget zone, TMH zone, thermomechanically affected zone, and heat affected zone, and the base material. BM is referred to the base material. So A figure, the base material average grain size is like 130 micron after FSP. D figure, you can see that room temperature FSP gives the grain size of approx 4 micron, and after that we perform the cryo-FSP. In E figure, you can see the grain size is drastically reduced to the 4 to 2 micron, and also we did misorientation and angle analysis. So we got the some improvement in the higher grain boundary misorientation after the cryo-FSP. A little bit, but we got the improvement. So after that we go for a SEM and TEM analysis, and you can see the grain boundary distribution. There are some in 5000 series there is some manganese rich and iron rich precipitates are present. So these are present near the grain boundaries in the as cast material, But after the cryo FSP, we got the distributed these particles with uniform distribution. So these are the ADS analysis with SEM images, and in right side you can see that TAM images, because we are not getting the nano silicon carbide morphology. In normal SEM we are getting the precipitates morphology, but not in depth, because nano size of reinforcement is added. So we go for TAM analysis. Here we did room temperature. RT is referred to room temperature, CFC is referred to the cryo FSP. So we already confirmed the grain from the microstructure that grains are reduced to 2 micron. Here also it is showing, and also some morphology of precipitates are observed. So this shows the uniform distribution of these particles. But in SAD pattern, you can see the dark field and bright field image. We analyzed the SAD pattern and calculated a D-spacing between the interplanar spacing, and we confirm that silicon carbide is present near the grain boundary, and which creates the pinning effect and which gives the better properties in terms of mechanical properties. So these are the figures of comparative figures of room temperature FSP and cryo FSP. Then after we go for mechanical properties, we did Vickers hardness test of 5 kg of load and 15 second dwell time. And in 4 sample, the cryo FSP shows better hardness properties. Then we perform the mechanical properties like tensile test, uniform tensile testing, in which you can show the red graph shows the cryo FSP sample, shows the better mechanical properties in terms of room temperature followed by still testing followed by room temperature. So as cast material has some porosity and voids, so some sudden fracture has been occurred. And after testing the tensile sample, we go for the fractographs analysis, in which fractographs you can see a figure, the dendritic arms, which is present in mostly in as cast material, and then go for the B, which is the as cast of composite material. Then C and D shows the fine dimples, which because of the ductility has been increased and the fine distribution, fine equivalence has been observed in the cryo FSP method samples. And then after we did the experimental value and theoretical value comparison, we calculated all the strengthening contribution, and then comparatively we got some improvement by the theoretical and experimental. There are some errors because XRD data we are calculating the dispersion strengthening, dislocation density, and grain boundary strengthening. So there is it also correlated well with the our fractograph and tensile properties. So overall summary of my work is that we firstly developed the aluminum 5083 nano reinforced composite, and then we go for characterization of mechanical and microscopic properties, and we got the fine distribution of precipitates and intermediates and nano reinforcement, and then we calculated the strength like mechanical properties, which is improved in case of cryo FSP due to higher cooling rate in cryo FSP method. So and also strengthening mechanism has been correlated with the mechanical properties. So I would like to acknowledge all the funding agency like CSIR, MST, and my department, my college and DORA office, and my supervisor also, my junior, my parents and my colleagues. And at last, thank you very much. I would like also thank my Honorable Prime Minister Narendra Modi ji, because in this year we are hosted the G20 summit, and which is proud moment for us that India successfully hosted the G20 summit. Thank you very much. Thank you, sir.
The presentation is open for discussion. If you have any questions.
Gaurav, it's nice presentation. Like you have done this ethanol and liquid nitrogen used for
Methanol plus liquid nitrogen.
Okay,
Yeah.
methanol plus liquid nitrogen for this cryo FSP, and it was showing like minus 35 degrees centigrade the temperature, and you're showing in temperature profile it is much drop like 50-60 degrees centigrade as comparison to room temperature FSP. Is it feasible like to if you supply the liquid or like at minus 35 degrees centigrade and it is reducing like minus 60 or minus 70 degrees centigrade the temperature?
It depends upon the heat generated during the FSP.
So
Actually, in room temperature, we are not providing any back cooling or only air cooling is there. In back cooling, we are providing additional drop of temperature. If there is larger difference between high temperature and lower temperature, the cooling rate will increase. If air is at 23 degrees centigrade, but now the backing plate is used and flow is going on, and so temperature is backing plate is large. So if it is generated like 500, 450, then drop will sudden.
so that backing plate is that much effective to
Yeah.
reduce this much temperature?
You can say that copper material is used for the backing plate. So conductive material that we can easily conduct, and also the conductive paste is used, so that easily heat is dissipated through the working plate and the flowing material.
The second thing, how much grain size reduction you have observed in this like after cryo FSP?
I already mentioned like 50%. Firstly, in room temperature, that 4 micron we are getting, and in after cryo-FSP, the 2 micron grain size.
Sure, but it's not like looking like correlating to the tensile strength. You're reducing the grain size completely half, and the tensile
Yes.
strength is much
We
that much incremental.
Yeah, you are right. Actually, we are calculating the grain size strengthening individually. You can see that here. There, grain boundary 150, 110, and 155.
Yeah.
So by this formula, it is showing improvement.
Yeah.
Like 240 is coming, 295 coming, and also room temperature 190 is coming, and also 230 is coming.
No,
So
like just go back. Here it's showing 110 and 155.
yeah.
So like it's around
There is
45 kPa.
we are calculating nugget zone, which is a common zone, and it is calculated by formula. There are some errors like in calculation of XRD data, and we are getting data. So that is increasing trend. So that is better.
That is there, but
correlated.
if you use simple half patch equation,
Yeah.
you using same constant and same thing, you putting like 4 micron in the
Yeah.
in that equation, and then you putting 2 micron in that equation. How it is?
Yeah. You are saying it by the formula only.
So you
We-
have calculated using.
Yeah, using formula, and that value we are getting in room temperature, that is based on the nugget section of the material.
Okay.
In tensile sample, we have extracted sample from the nugget section.
Okay.
So we calculated this value 193 and 230. This is experimentally value.
Okay.
We have done multiple time of testing. We cannot go for like strengthening shows that 200 we have to go for 200. No, it is experimentally coming. It is some minor like 20 or 15% diversity is there, but we are getting the trend only.
Okay. Thank you.
Yeah.
Thank you.
I have a couple of questions. First of all, yeah, nice work, Gaurav.
Thank
Just building on the Pratap's questions, I think that's a nice point, like he mentioned. The temperature, so you are actually flowing these liquid nitrogen and trying to maintain a constant boundary condition, constant temperature boundary condition, right?
Yeah.
35, minus 35 degree, whatever. Now, what is the temperature you would expect at the surface of the workpiece? Don't do any processing.
Okay.
Just with a simple heat transfer calculation, right? There's a thickness of the base plate,
Yeah.
then there's one more sandwich, that copper plate, then there's your workpiece has
Yeah.
some thickness, right? Now, you have a constant temperature boundary condition and you're maintaining that temperature, okay, fine. What would be the temperature you expect at the surface?
Okay. And
So, I mean, that's one thing. Because now, if the heat is continuously generating, so it's the constant flux is there, constant temperature boundary condition is the other. So, can you, or have you thought or did something like some heat transfer analysis to maintain or see what is the temperature you will get at the process chain?
Nice, thank you. Firstly, I will answer the first question. You are saying that without going for processing, I measured the temperature because in backing plate there is a minus 35 degrees centigrade is there. And on the top of the surface it is like 0 to 5 degrees centigrade. The plate we do not go for equation. We calculated the temperature by using the thermocouple. It is showing like a 0 degree to 5 degree range. So there is a heat drop without processing.
Yeah.
So then second option, you are saying that to calculate the heat equations and what are the thermodynamics,
Yes.
dynamics there.
I think the simple calculations if you do,
Okay.
because if your cooling rate plays a role, right, then you might, if you reduce the temperature of your fluid,
Yeah.
or you cool it faster,
Okay.
you might expect different
Yeah.
grain structure altogether, right? So those things, I mean, can be thought. What do you think?
Yeah, and right now I don't have much idea about that, but definitely I will learn and then improve
Yeah.
my knowledge
I think yeah, that
and
could be
also add with this work.
good. And one more, sir, just one additional question. This that's a rather naive question as well. These SiC particles, are they undergoing melting and then
No,
like
the
crystallization?
temperature is the melting temperature of SiC is very high.
Quite high, right?
So that
So
is
they're
not
just
possible.
dispersing into the metal.
Yeah, dispersing is something. It will give the
Because
dispersing.
there were some spherical particles.
Yeah.
I thought,
After ball milling, there is mostly the spherical particle has been observed, so that nano reinforcement is not melting, but it
so
is.
what is the typical these surface energies of these particles, like, because that would determine the bonding strength between these your matrix phase with the reinforced phase, right? This interface adhesion or whether so it would depend on the surface
Yeah.
energies of
In
those.
spectrograph, we have observed some silicon carbide near the grain boundaries, but not calculated the energy, how much amount. But silicon carbide is like a grain boundary pinning effect is there, so that fractured surface showing that. But I don't calculated the exact interfacial energy and some particle.
Yeah. Thank you.
Thank you, sir.
Yeah, I have one question. Have you tried varying the silicon carbide volume fraction?
Yes, sir. Firstly, I optimized the silicon carbide weight percentage. In my first paper work, I performed like 1%, 2%, and 3%. And from out of 3 composition, we got the best properties in 2 weight percent. So this work is only based on 2 weight percent.
Can you go a little higher, like?
Yeah,
How high can you go actually?
Actually, in 3 weight percent, we are getting not good properties. Some clusters and some inhomogeneity structure has been
Oh,
observed.
so when you increase the silicon carbide content,
Yes, sir.
there's a tendency to cluster more, or?
Yeah, in some reasons, because in FSP process during in ester casting it is present in clusters, but in FSP process because we are going for ester casting followed by FSP. So in this method we are getting inhomogeneous microstructure. Some grains are larger, like 10 micron grains are coming, and in the nugget section more finer, like 2, 3. But some sub grains are also observing, so not getting homogeneous microstructure. That's why we eliminated the 3 weight percent, not go for 5%, 4%.
So this is your thesis work, is it?
Yes, sir.
Yeah, it's a good effort, and you have done lots of work.
Yes. Yes.
Any other questions? I have a couple of questions. One, maybe I missed something. Do you have a comparison of AA5083 versus the silicon carbide dispersion base material properties?
Yes, sir.
You have?
Yeah, here I did not show. Firstly, make without reinforcement A50 and with the 3 weight percentage, like 1%, 2%, 3%, and then room temperature plus ester casting, then cryo FSP plus ester casting. Then I made 5 composition, like then all properties I have checked.
What is the percentage increase you got in the best one? What you chose compared to the base material?
Base material we are getting 153, which is common tensile versatile properties of IS we are getting in 5000 series, and when we increase to 1.8%, it will go like 170, 173, and then in 2.8% in room temperature we are getting 190 something, and after that there is some sample like we are getting properties, but not sudden fracture is coming and no ductility, some ductility is not coming, yield strength is coming but no ductility is coming, so strength will increase but not in proper manner. So we eliminated the 3-weight% and then go for 2-weight% plus cryo FSP, because coarsening and grain growth are also major dominating phenomena. That's why we go for that.
But I see in some places it's reporting yield strength at 228 and even just based on it.
So in my case, we have developed stress casting lab facilities in own lab, and in stress casting, in every fabrication we are getting not getting the same composition as the other. We are getting like stress casting. We read the paper like 150, 152 around without reinforcement we are doing. But I don't know that. Maybe they are used ultrasonication with the stress casting, some vibration, and some more method. Compo casting has been used. Like it is also case of stress casting.
Different temperature condition.
Different temperature condition also. That may give more improvement.
And another question which I'm not very sure is you are talking about the grains and sizes 4 microns, 1 micron, something like that.
Yes.
But what about the dendrite structure and grain and what? Is there any differentiation that you have shown?
Yeah, in microstructure I have shown, because in cast structure generally dendritic structure occur.
So towards the end you are talking about dendrites, but before that you were talking about as if it was equiax grains kind of thing.
Yeah.
So if you can clarify to me what that is.
Actually, the composite produced here room temperature FSP plus stress casting, and then stress casting plus cryo. There's two methods we produced, but the basic is as cast. So we have to also compare the value of as cast composite and the room this combined method of FSP. That's why in A figure without reinforcement base material is there. So dendritic structure is obvious in stress cast. Then we added the silicon carbide. Then also dendritic structure in nanocomposite, but in room temperature FSP. So dendrites are eliminated due to severe plastical formation, and also the cryo FSP case the same dendrites are eliminated, but the fine grain structure has been eliminated due to higher cooling rate during the flow. That's why. Thank
One
you.
question I have is how cryo is helping you?
Cryo
What
is
is the effect of cryo?
Yes, sir. Thank you. Actually, the cryo is only reducing the peak temperature to the room temperature cooling. If we perform the FSP, if there is no cryo cooling, room temperature is cooling is there. So peak temperature, let's suppose in nugget section that 550 temperature is generated. So there is a temperature difference 550 to 220 to let's suppose 27 is the room temperature. So time is also taking enlarged, and grain growth, it will give the grain growth. So grain size will increase, and which gives the lower strength. Which when we use the cryo FSP or cryo cooling, the temperature is already dropped like minus 35 is not getting. We are getting the temperature on surface is 0 to 5 degrees centigrade. So the temperature drop between high temperature and difference. High temperature to base plate or surrounding temperature is high. So sudden cooling is there. So there is less time to grain growth or precipitate growth. So that's why the higher cooling rate gives the better properties in cryo FSP.
Yeah, that's where if you talk about cooling rate, right?
Yes.
Now, how do you play with the cooling rate? If you do some calculations, some numbers you have,
We inserted the thermocouple. 3 position we inserted the thermocouple.
Right now you have calculated it.
Yeah.
But just which now you can't run the experiment for all the cooling rates, right?
Yes, sir.
So just a priori, if you do some calculations like this is the heat flux and constant boundary conditions, what is the cooling rate you will get? Right?
Okay.
It's simple enough to calculate. Then you play with the heating rate and cooling temperature, right?
Okay.
And the difference, the thickness of the workpiece, all those.
Definitely, I will. Thank you.
No more questions. Your talk has generated a lot of interest. Thank you. And we have to move on. The next one is cancelled. That is energy absorption property of aluminum foam developed by reinforcing aluminum alloy LM24 with the